I am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will see the topic on Faraday's law and displacement current for the course Electromagnetic Fields and Waves. So, in electrostatic and magnetostatic fields, the fields are considered as time invariant or they are also called as static fields. But in time varying or dynamic electromagnetic fields, the electric and magnetic fields are interdependent. The static electric fields are produced by stationary electric charges and the magnetic fields are produced due to motion of electric charges with uniform velocity or the magnetic charges. The time varying fields are produced due to time varying currents. Faraday's law was given by the British physicist and chemist Faraday, and he is a great experimental scientist. His contributions to early electricity includes invention of motor, generator and transformer, electromagnetic induction and law of electrolysis. And according to Faraday's law, the static electromagnetic field cannot produce any current flow, but with the time varying field, an electromotive force EMF induces which may drive a current in a closed path or a circuit. So this EMF is nothing but a voltage that induces from changing magnetic fields or motion of the conductors in a magnetic field. The Faraday discovered that the induced EMF is equal to the time rate of flux change of magnetic flux linking within the closed circuit. So the Faraday's law can be stated as E is equal to minus N into d phi by dt volts. Here N represents the number of turns in the circuit and E is the induced EMF. And suppose if there is a single turn circuit, then N value becomes 1, then the Faraday's law will be given by E is equal to minus d phi by dt volts. So the minus sign indicates that the direction of the induced EMF is such that produce a current which will produce a magnetic field which will oppose the original field. But in 1834, Henry Frederick Lenz postulated the law. Thus, according to Lenz's law, the induced EMF acts to produce opposing flux. So now consider the Faraday's law. The induced EMF is a scalar quantity measured in volts, and this induced EMF E is equal to integral over the closed surface E dot dl. Here E is the electric field. The induced EMF in equation indicates a voltage about a closed path such that if any part of the path is changed, the EMF will also change. Now the magnetic flux denoted by phi passing through a specified area is given by phi is equal to integral over the surface area B dot ds. That is the magnetic field surface integral give the flux, and B is magnetic flux density, and by using the result we can write the EMF as E is equal to minus d by dt integral of B dot ds. So finally we can combining the equations we get the electromagnetic force EMF is equal to integral over the closed path E dot dl or minus d by dt integral over the surface B dot ds. And now there are two conditions for the induced EMF. The first condition is the closed circuit in which EMF is induced is stationary and the magnetic flux is sinusoidally varying with time. So for this case, the magnetic flux density is the only quantity varying with time. So we can use the partial derivative to define the relationship as B may be changing with the coordinates as well as the time. And here we can write E dot dl integral over the closed surface is equal to minus integral over the surface dou B by dou T dot ds. So this is similar to transformer action, and the EMF now is called as transformer EMF, and we know the Stokes theorem gives the line integral how can it be converted into surface integral as integral over the closed surface del cross E dot ds equal to minus integral over the surface dou b by dou t dot ds. So here the both surface integrals taken over the identical surfaces. So by removing the integrals we can write del cross E dot ds equal to minus dou v by dou t dot ds, or we can write del cross E is equal to minus dou v by dou t. And this equation is one of the very famous Maxwell's equations, and if B is not varying with time, the equations give the results obtained from the previous equation of electrostatics, that is integral of E dot dl equal to 0 and del cross E is equal to 0. And now we see the second condition. So the magnetic field is stationary, constant, not varying with time, while the closed circuit is revolved to get the relative motion between them. So this action is similar to generator action, hence the induced EMF is called generator EMF or motional EMF. So now considering the charge Q is moved in the magnetic field B at the velocity V, then the force on a charge is given by F is equal to Q into V cross B. And the motional electric field intensity is denoted by EM, and it is the force per unit charge, that is E by Q, and we can write this as V cross B. And the induced EMF, now we can write integral over the closed surface EM dot dl is equal to del cross B over the integral dot dl. So this equation represents the total induced EMF moved in a uniform constant electric field. And if the directions of the velocity V in which the conductor is moving and the magnetic field B are mutually perpendicular to each other, then the induced EMF is given by V is equal to BLV sin 90 degree. We know it is sin 90 degrees 1, so it is BLV. Here L represents the length of the straight conductor. So now the third condition, in case the magnetic field density is also varying with time, then the induced EMF is the combination of transformer EMF and the generator EMF, and is given by integral over the closed path E dot dl is integral of minus dou v by dou t dot ds plus integral over the closed surface V cross B dot dl. So Faraday's experimental law has been used to obtain one of the Maxwell's equation in differential form as del cross E is equal to minus dou v by dou t. So we can understand from this equation a time varying magnetic field produces the electric field. And now we are moving to displacement current, and from the point form of Ampere's circuital law, it will be applied to steady magnetic fields as del cross H is equal to J, and by taking integration we get del dot of del cross H is equal to 0, which is equal to del dot J. And the divergence of the curl, we know it is 0, so del dot J also 0. But according to the equation of continuity, del dot J is equal to minus dou rho V by dou T, and if dou rho V by dou T is equal to 0, then we can write the equation as del cross H is equal to J plus G, and again taking divergence we have 0 is equal to del dot J plus del dot G, or we can write del dot G is equal to dou rho V by dou T, and del dot G is dou by dou t of del dot d or del dot dou d by dou t. So this G can be equated to dou d by dou t. So now Ampere's circuital law from point form is del cross H is equal to J plus dou d by dou t. So this additional term dou d by dou t has a dimension of current density, which is represented by amperes per meter square, because it results from time varying electric flux density or displacement density. So Maxwell's termed it as displacement current density, and it is denoted by JD. So now in a material in which sigma is equal to 5 S per m and epsilon are equal to 1 and E is 250 sin 10 power 10 T, the conduction and displacement current densities are found as Jc. The conduction current density is from the formula sigma E, that is conductivity multiplied by the electric field, and displacement current density is obtained from the formula JD is equal to dou D by dou T. Thank you.